During the Apollo era, NASA accumulated nearly half a ton of lunar rock and soil from 6 manned missions to the moon. Recently, for the first time in history, a relatively large sample of lunar soil was given by NASA's Johnson Space Center in Houston, Texas, for a purpose other than pure scientific research. The lunar soil was released to test its properties in making concrete as a possible future building material for a lunar base. The investigator receiving the sample was Dr. T.D. Lin, who works for Construction Technology Laboratories in Skokie, Illinois. From the 40-gram sample, Dr. Lin plans to make one 1-inch square cube and 3 mini tablets roughly the size of sticks of chewing gum. Basic engineering knowledge will come from tests that may relate the material's strengths to building structures, with an ultimate long-range goal of someday building a permanent station on the surface of the moon. Here on Earth, concrete is the backbone of our construction industry. The concrete used in pouring the foundations for this house had its beginnings in a quarry where many key ingredients are mined. Preliminary test results indicate that concrete made from lunar soil is twice as strong as that specified by standard American building codes and may need minimal processing. Concrete is one of several materials being investigated for building on the moon, according to Dr. Wendell Mendel, planetary scientist at the Johnson Space Center.
If you can make a brick on the moon and you don't have to import the brick from the Earth, then you've saved an enormous amount of money by not having to ship the mass through the transportation system. So that's a tremendous incentive for learning to use lunar materials.
NASA scientists feel that the very first base on the moon might consist of a series of modules brought to the moon's surface and buried in order to provide protection from cosmic radiation and the harsh lunar environment. After the base camp, there would be an evolving complex, depending very much upon lunar resources for building materials. One person very much interested in what this base might look like is Dr. Peter Land, an architect and professor at the Illinois Institute of Technology. His designs are simple, direct, low-slung buildings that consist of shielding heaped with lunar soil and independent inflated structures underneath, housing all lunar base functions. A small group of architecture students at the University of Houston has developed an 8-year program for setting up a manned base on the moon. Again, Dr. Mendel.
Using that scenario, they're beginning to work on point designs of architectural problems, and they hope to make that scenario and keep it consistent over a period of years so that other students in the department in future years will take it and build on it. And we look upon that as a nucleus of a very creative effort that will contribute a lot to our thinking about how to live in space.
By using computer models, Sam Jimenez maps out a configuration of 5 living and laboratory modules. Through time, these modules could be expanded to maintain 3 distinct areas, all linked together into a centralized base, but capable of growth if needed. Clusters of modules act as a foundation for larger inflatable environments that could be maintained for living quarters, experiments, as well as energy and crop production. The base would be shielded from cosmic radiation by bags of lunar soil heaped over the modules and inflated structures, with causeways to any section of the base. For many, the idea of building a lunar base seems very distant, but much of the technology exists today. When NASA's space station is in place, these pioneering efforts in engineering and design may become a reality by helping us establish a manned lunar base sometime in the 21st century.